Thank you. I want to thank Samsung for the invitation. I'm really excited to be here. Just to kind of give you a perspective of what I'll be talking about today, I'll be talking about work that's at the intersection of machine learning and symbolic logic. I presume most of you have heard of machine learning. Maybe some of you have heard of symbolic logic, and I'll try and motivate why this intersection is interesting and has something to contribute to the discussions of AI, especially about generality. Just to kind of give you a perspective of what's coming up in this talk, I'll start with some motivation. I'll give you examples of why this intersection and integration is interesting. I'll then talk about certain approaches we've been doing to address the problem of transparency and interpretability. I'll then move on to this notion of ethics and ethical responsibility, and I'll talk about what we've been doing in that regard, and finally conclude with some perspectives in conclusion. So why do we really care about this intersection and an integration of logic and of learning? As it turns out, logic and learning have sort of complementary aspects to both of them. Machine learning, as you know, is about induction. So looking at some examples, how do you extract patterns in functions, right? Whereas logic is really concerned with the notion of deduction, which means that if you have some knowledge, how do you infer new knowledge from it? Machine learning is about big data. And in contrast, symbolic logic is about assertions. For instance, I could tell you, I'm from the University of Edinburgh, and you don't need a million examples. One example will do. And we need a way to actually integrate that kind of information into the system when we talk about systems that work with human beings. The other kind of technical difference is that machine learning is typically concerned with what are called as independent and identically distributed random variables. What this means is that you have random variables which capture some kind of stochastic information about the world, but they're assumed to not be related to each other beyond a certain dependency that I'll go over. Whereas if you think about it, the world, and the world we're sitting in certainly, has a lot of relational structure. So what I'll really be talking about is how I've been using the unification of these two areas to look at these questions of transparency, interpretability, and ethical responsibility. Just to say that this is not a new area. In fact, this goes back to very early days of the philosophy of science, where people like Boole, Definetti, and Carnap have been thinking about what exactly does it mean to combine deduction and induction. In the AI, there have been a whole bunch of different areas that have kind of fallen into this camp, like relational learning, statistical relational learning, and so on and so forth. And really, the point here is that they have been motivated by these two critical aspects. One aspect is that the world is relational, and the second aspect is that you often need to reason about hard and soft constraints. In fact, constraints came up in both of the earlier talks, where you have some kind of soft knowledge and you might have some hard knowledge, and you want a machine learning model to be able to handle these kinds of constraints. So just to see a very simple example, the image here is a bit grainy, I'm sorry for that. But what this is capturing is gene expressions and gene-protein interactions. And if you look a bit on this figure, what you see is tissues, proteins, genes, and there's certain interactions between them, and there's a certain kind of relationship between these different entities. Right? Given this kind of a structure, the questions you might be interested in is things like, is gene X involved in contributing to some disease Y? What is the probability of this involvement? If you condition on Y, so if you set this disease to be true, what other genes might be related, might be influencing this disease? And finally, if you want to look at certain subgraphs to identify and study this disease, which of the subgraphs are interesting for you? Okay, so these are the kinds of questions that a data scientist might have in mind when he's dealing with this kind of data set. Let's look at another example. So this is essentially what is a Markov network. People also refer to this as a conditional random field. And what this is saying is that it's talking about how smoking might be a social thing, okay? So it's a social network for smoking. And it's basically saying that if somebody's a smoker and they're friends with somebody else, then that other person is also likely to be a smoker. Okay? Notice that this is not a hard fact, right? It's not the case that every smoker influences every other smoker, but there's a certain probability of this happening. Okay? Similarly, if you smoke, you tend to cough. There tends to be a coughing pattern. And again, this is not an absolute fact. Perhaps if you've been smoking for a very long time, then maybe coughing is an absolute thing. But in the early durations, it's a probabilistic fact. And given this kind of network, you have a bunch of different questions you might be interested in answering. And in fact, you might even want to change the graph. At some point, you might want to say, I'm not just interested in understanding how smoking permeates in social networks. I also want to understand how it works in a family. For instance, if a child sees a parent smoke, does it mean that the child has a certain propensity to start smoking as well? So you might be adding new knowledge, and the idea is that by using symbolic constraints, you don't have to go back and change the graph. You would just be adding this knowledge. There are certain kinds of queries that you might be interested in. The most standard thing would be evidential. For instance, you see that A is friends with B and that B smokes, and you're kind of interested, well, does A smoke too? And you're interested in the probability that A smokes. So, because this is a statistical assertion that you're trying to make from this data. You might be interested in causal information. So, for instance, if I smoke, what is the probability that I'll start coughing? Right? Two other kinds of very interesting and actually slightly more complicated questions require more information than that was present in the previous graph. And these are interventional and counterfactual queries. Okay? Interventional queries basically says, imagine now I start to reduce the amount of cigarettes I smoke by half. What is the probability about me still coughing in 6 months? Right? A counterfactual basically says, imagine I never smoked, would I still be coughing? So do I have some kind of condition that causes me to cough even when I don't smoke? Right? And counterfactual, of course, requires some kind of hypothetical reasoning. So these are slightly more, as I mentioned, complicated questions referring to the causality of this domain. I won't go into so much detail and discussion on those, but this is just to point out that these are interesting questions that current machine learning models are really struggling to answer. Okay? And again, I want to point out that we're not just interested in writing this down. You want to learn this from data. And really, the exciting thing for me is how do you combine expert knowledge where it's available and information from data that you can learn from. Okay? It turns out that these questions are quite pertinent now because there have been a bunch of interesting observations made in the machine learning community. You might have all seen this figure here. So this is why adversarial training was kind of motivated. And the observation is that on the left image, you have a panda, obviously. You would agree it's a panda. I would agree it's a panda. But the system only reports 57% confidence. You add an amount of noise, right? And the system now thinks this is a kind of ape with 99% confidence, right? And this is really alarming because if you think about it, if you think about a self-driving car that potentially confuses a road surface marking for a child, then you could imagine, or a child for a road surface marking, you could imagine the disastrous consequences of this. A second kind of very similar example, people found out that when they trained this machine learning model on hospital data, the model was seeming to predict that people who were asthmatic, the probability that they would die of pneumonia was lower than people who don't have asthma. And this is a very counterintuitive observation. And in fact, this is wrong. And the reason this machine learning model was suggesting this was basically because it turned out that there was an aggressive policy in the hospital to provide treatment to people with asthma. So because they were getting this aggressive treatment, the probability that indeed, statistically speaking, that they would die of asthma was much lower when you looked at the numbers, right? So it's quite difficult, if you just look at the black box machine learning model, it's very difficult to contextualize it, and often it's the job of the engineer or the scientist to actually do this and figure out the contextualization. And what I'm suggesting here is that symbolic logic provides a kind of more rigorous and systematic way to tackle these issues. If you think about the use of AI in society, it's no longer just about accuracy, and this was something that even Noah was mentioning. In fact, there are pedagogical reasons about involving AI in society. For instance, in game playing, it's not enough that you beat the best player. You kind of want to know, what is the strategy? What is something that I can tell a person about what the right thing to do is? You might want to, in self-driving cars, you might want to figure out, when do I swerve? When do I accelerate? When do I decelerate? In tutoring and interaction, you often want a model of the student or the user so that you can have a more natural interaction. And again, in language and vision, again mirrored in the last two talks, the notion of semantics keeps coming up. How do you understand what the image is talking about? How do you understand what the video is talking about? There are also legal and ethical reasons. In fact, I work with a lot of banks now, and one of the concerns is if you find out that the credit card application was denied, what is the reason for this, right? A self-driving car causes damage, and you often want to know, like if you imagine an ordinary car causing damage, the person you go to is the manufacturer. So what will be the case when you consider an AI system, right? So it's not sufficient to say that something was acted in good faith. You need to understand the principles why a decision was taken. So I'm not suggesting, again, that we have solutions to all of these problems. I'm simply suggesting that we need to look broader than purely looking at statistical associations to understand how all of these things can be addressed. And really, to me, they represent as opportunities. Opportunities in the sense that you want to accept human input in the form of hard or soft symbolic knowledge. You want to enable some kind of context-dependent and user-specific interpretability. And finally, you want to reason about semantics, choices, and models. And all of this falls in the domain of logic. So what I'm arguing for is really hybrid systems that integrate this for a more systematic way to tackle these deeper challenges, okay? So I present here 3 strategies. This is something that we've been looking into, my team and I. And all 3 strategies, I think, provide some kind of contribution to understanding how the bridge between the 2 areas of logic and learning can be brought together. Okay? So one thing is that people often complain that logic is discrete and noise-free, so you can upgrade them. And in fact, the Markov network that I showed earlier is already an example of how you can add noise to the model. The other kind of thing you can do is you can try and integrate low-level reasoning and low-level learning and high-level reasoning. And finally, you can find a way to inject symbolic knowledge or extract symbolic knowledge from machine learning systems. And I'll show examples of that. Upgrading to noisy and continuous. Now, just to put this in context and to simplify what we're talking about, let's just see a very simple example of pure noise-free symbolic constraint, okay? So this is basically saying every person is infected. And if you get in contact with some other infected person, then the second person is infected too. This is a good constraint, but this is not always true, because as we know, just because you get in contact, it doesn't mean that infection would necessarily come to you. And infection, not every person is infected. So what you might want to say is that the 10% of the population is infected. Right? And this would be a very simple extension to the previous program, adding these probabilities, and you get essentially a noise model. To do something slightly more non-trivial, imagine now I want to talk about the distribution of blocks in a room, okay? And what the first constraint is saying is that all objects, there are n objects in the room, and all of these objects, about 30% of them are made of wood, and 70% of them are metal. Okay? That's the first constraint. What the second and the third constraint is saying is that if your object is a metal, then the size of it is drawn from one of these beta distributions. And if it's wood, it's drawn from another distribution. So you're basically able to capture a fairly complex scenario with different blocks of different sizes using 3 lines of code. To kind of see where this really comes into useful, one of the things we were interested in is trying to understand how you could integrate reasoning into sensor fusion. Now, we all have really good state-of-the-art, object detection systems, right? So if you gave these 4 images on the bottom to an object detection system, it's kind of clear what the system would do, right? On the first image, it would say there are 2 objects. In the second image, it would say there's 1 object. In the third image, it would say there are 2 objects again. And the last image, it says 1 object. Right? But of course, as a human being, if you're watching this video, you understand that in fact the objects are being placed inside the other object, right? So how do you get a machine learning system to actually understand this? It's quite simple. You inject these constraints into the learning system. Okay, so what are these constraints saying? The bottom constraint, which is a bit easier to read, is basically talking about the transitivity property of objects, right? So if one object is inside another and the second object is inside a third, then of course the one object is also inside the third. This is something that you and I understand, and it's something we can give the machine learning system. The constraint at the top is a bit harder to read, but basically what it's saying is that if I place an object that's smaller on top of a bigger object, there's a good chance it's going to fall in, but also it might fall off, right? So this is, again, a very commonsensical thing that you and I understand, by injecting these constraints into the learning system, you can actually get the robot to correctly predict that the smallest object is inside a bigger one. So this is a way you can get common sense into a particle filter, for instance. Some other work we've been trying to do in trying to understand how we can integrate low-level learning and high-level reasoning, we've been looking at question answering. So this is a problem at least I encountered in high school. Maybe some of you did too in Korea. I'm not sure what test you have before you get to the university. But typically, this is a kind of a combinatorial problem, right? So you have a bunch of marbles, you take some out, and you observe something, and you're interested in the probability of what you observed and what's inside. Okay? And if you look at this question, again, this is a probability question, it's quite interesting because there's a clear structure here, right? There is a model, there is some kind of conditioning, which means that you place some evidence, and then you're interested in a query. And how would you solve such problems in a general way? We kind of take the approach again with programs where we do syntactic parsing. The syntactic parsing is basically giving you the linguistic structure in the question. So, for instance, there's a bag, which is and there are marbles and so on and so forth. And then we map this syntactic structure to a combinatorial structure, which basically tells you how you divide up the bag in terms of marbles. What happens when you observe something? And if you see, this combinatorial structure is really giving you all possible worlds in terms of what's happening when you observe something. And indeed, this can be represented as a very simple program. So if you think about this, this is completely automated. So if you're imagining an intelligent tutor, or you're trying to train students to understand and solve these questions, what is really happening is that these questions are being mapped into the programs. The programs gives you the solution. So you have a kind of explanation about what really happened. One of the questions, of course, is that you want to avoid humans providing the symbolic knowledge as much as possible. And so the question is, can you learn these programs from data? In a way, learning programs is very similar to something like learning finite state machines in linguistics and many other domains. Similar problems pop up. And so to kind of give you a context of what exactly we mean by learning programs, this is the tabular data about student enrollment, the courses they're taking, and the grades they've obtained. Okay? And you notice that there are many different things happening. I've indicated this in colors. So for instance, what's happening in the orange column is that there's a certain distribution which captures the grades between low, middle, and high. If you look at the blue column, it's telling you the IQs. Again, a continuous distribution this time. And if you look at the green areas, and this is not just one across the row, what you're trying to understand is how does the length of the course influence the grade, right? So you want to actually build a generative model for this data, which means you want to construct a probabilistic generative model that can reconstruct this data, right? And you might have other background knowledge. For instance, you could have, so if you're talking about a university context, you might say that, for instance, no first year is allowed to take a course that goes beyond 90 hours, right? So we propose this program induction approach, where basically what's happening is that we learn we do density estimation for the individual variables, and then we do associative rule mining to actually figure out a program that you can basically read. A course administrator can read this program to understand the patterns that are emerging in the data. When we did this work, what was interesting to us is that, of course, this program is in some sense interpretable and understandable, but you can imagine this kind of nightmare scenario, right, where you construct a program that's so large and so massive, you're completely lost. And even though in principle, this is somehow understandable, you're not able to make head or tail of it because the patterns are so complex. So one thing we started to think about is why focus on learning interpretable representations when you can instead focus on querying, right? If you think about how Google interfaces with you, you don't really care about the internal decision-making structure of Google. In fact, if it presented it to you, you'd be confused. What you really care about is the fact that you can type a query in and get an answer out. So we started to think about this idea of expressive querying, which means that you can ask a probabilistic query, but you can throw in these constraints in a very rich language, often with logical connectives. So you can conjoin them, you can disjoin them. So for instance, I'm simply asking here, given that if the number of hours of a course is greater than 200, what is the probability that the student is satisfied with the course? Right? A simple question. You could go back into one of those programs and look at these programs manually, or otherwise, you could simply give me a probability here to just give you a sense of how the data is distributed. And now, interestingly, once you turn to this idea of only asking queries, you often worry about other kinds of things. For instance, how do I make sure I can answer these queries quickly? Right? So a computational scientist would kind of take that insight and say, how do I answer this question efficiently? Right? This is a computational notion of what does it mean to say that some query answering is efficient. And one way you can think about formalizing that idea is that when you want to answer a query, you simply do one pass over the network or the representation. Right? In this sense, neural networks are efficient. Not in the learning phase, but in the query phase, right? Because if you pass an image, you'd simply pass the image through the neural network, and it tells you, is this a cat or a dog? Right? Trying to understand, formalize that idea in this probabilistic context has led to some interesting work. And really, the bottom line for this comes from this insight that if you take these different kinds of probabilistic relational models, like the one I presented with the smokers, when I presented the program, all of these turn out to be really just the same problem. They are abstractly defined as what is called as weighted model counting, and one way to actually do this is referred to as by a knowledge compilation. So basically, in knowledge compilation, what happens is that you take the program, you take the representation, you construct a kind of circuit, and I'll show examples of the circuit. The interesting thing is that the circuits are expensive offline, okay? And this has to be the case. So this is because probabilistic reasoning is, in a sense, intractable, because you are reasoning about all possible ways you can change a random variable. So in its nature, it's intractable. But the interesting thing is once you build a circuit, answering queries on this is extremely cheap. So it's a bit like trying to really guess the number of layers of a neural network. That's roughly what it amounts to, okay? And the question we've been wondering is that can you learn such structures efficiently? Here's a very simple example of how this works. On the left-hand side, you have a Bayesian network for essentially your observation for rainbows, given rain and the amount of sunlight, right? And you take this Bayesian network, and typically in the AI class, what you often reason with are these kinds of conditional probability tables, which tells you the probability that a rain happens or doesn't happen, so on and so forth. And this can essentially be constructed and compiled into this circuit on the left-hand corner. What you see there are a bunch of variables. Think of them as really inputs to a gate. You have AND gates and OR gates, okay? And this is what I refer to as a circuit, okay? And it's also a probabilistic circuit, which means that probabilities also feature in the way the inputs are combined, and this essentially gives you an equivalent representation for the Bayesian network, okay? Another very, very related representation is one of these things. These are called sum product networks, and in contrast to the previous ones, where you had ANDs and ORs, you have sums and products here, and the idea here is that you use one of these representations to capture weighted sums of distributions. Okay. What is really powerful about both of these models is that computing these probabilistic query just simply amounts to doing one pass over this network. Now, if you want to contrast it with classical deep learning models, classical deep learning, of course, is geared for classification, which means you're interested in the probability of some label y given x, whereas what you're doing here is you're really doing generative modeling. So you're really learning the joint distribution over the variables. So it's much more powerful, and I'll show you an example of how we're using this to attack the problem of interpretability in classical deep learning. So we've been doing various extensions with these, improving the capability. So one of the things we've been doing is, how do you get these networks? Again, because these networks are inspired by logic, they remain discrete, although they can handle noise. So one of the things we've been trying to look at is, how do you handle continuous data? So if you think back about the student example that I had about courses, and the IQs, for instance, were a continuous distribution, you could capture one of those with these one of these probabilistic deep networks. Another kind of problem we've been looking at is, how do you deal with missing data? And often data is corrupted, right? And this really creates a problem for robustness, because if you know that the data is corrupted, you might try to impute certain values, and this can be problematic if you don't really understand where exactly this data is coming from. And so we have been extending these networks to essentially not just deal with one single probability, but actually have an interval. And the interval kind of corresponds to all possible ways you can complete the data, right? So what you're getting back is not a number, but you're getting a confidence interval, right? Which is a much more robust way of actually interpreting the data that you have at hand. A project that we've been looking into recently is by trying to use these networks to understand what's happening in deep learning. And how would we do that? So I'm assuming most of you are familiar with this notion of an autoencoder. So an autoencoder is a very old idea, despite recent advances. And really what an autoencoder is doing is that it's trying to do dimensionality reduction. Okay? So you basically have some kind of input, and you have a feature layer that is able to reconstruct this input. And of course, the trick here is, by making this feature layer interesting and compact, you can basically get a very massive dimensionality reduction. Okay? So what we try to do here is try to understand, what is this feature layer really capturing? What kind of information does it have? And how can you use this information to do something interesting? So roughly, the pipeline we have here is that you have this data. You use the encoder to essentially it's a joint, you use the loss function to kind of characterize what this feature layer would look like. And we take this feature layer and build one of these circuits, okay? So what would you get from this? Again, recall that in contrast to classical deep learning, which is geared for labeling and classification, you're able to get a generative model using this approach. And to kind of give you a perspective of what we're able to do, in classical deep learning, you'd pass an image, and it'll tell you, for instance, this is a 1 or a 0, or this is a shoe or a shirt or whatnot. But here you can actually get the network, get the circuit, to tell you what are the prototypical images for a certain label. What do 3s look like? What do 2s look like? What are the tokens that tell you for a given label? So for instance, what you see here are for the image 3, you were able to reconstruct what the network thinks is a 3, right? And this is really powerful, because now you really have an understanding of what the network is capturing, and at least at a human inspection level, you can kind of satisfy yourself by saying that this has learned the right thing. Right? This is something that people did worry about deep learning back in the 80s and the 90s. How can I make sure, even if I get really high prediction accuracy, how can I make sure it really learned what I wanted to learn? And using this, you can now get these images out, and you can kind of see, is it right, is it wrong, is this roughly what I imagine, right? So you can generate prototypes. And because it's, again, a logical circuit, you can do all sorts of fancy logical things on it. So for instance, this is something you can do where you fill in the blanks, okay? So many of you may have heard of the XOR function. In fact, I chose XOR here because it's particularly interesting from a neural network perspective. So perceptrons, for instance, in the 60s and 70s, one of the reasons research died out on them is because they were shown to not be able to capture the XOR function. And what the XOR does is basically it gives you a 1 every time the inputs are different. Okay? So if it's 1 or a 0, you get a 1. If it's a 0 and a 1, you get a 1. But if it's 1, 1, you get 0. And if it's 0, 0, you also get 0. So they have to be different, okay? And what I'm trying to do here is I'm trying to say, I give this image on the left-hand side in the little bounding box. I have this XOR function, and I'm forcing the classifier to tell me how can I get a 1 given that my first image is a 0, okay? And this network correctly generates the images that complete this task. Okay, so it's fill in the blanks. Similarly, if I on the bottom left-hand image, you have a 0 and a 1, 1, and you're trying to generate an image corresponding to the first input. And on the right-hand side, it's essentially the same task, but now I flipped it. I want the output to be 0, which means that 2 images must be the same. There have been some recent developments. I won't go into that for the interest of time. But one thing that we've been wondering is that how expressive are these tractable models, okay? So as I mentioned, you have a Bayesian network, you do all of this compilation, you get one of these circuits, but how powerful are they? What can they really do? Can they do causal reasoning? So by causal reasoning, I really mean the question of computing interventions. So for instance, if you think back about the smoker example, I'm interested in the query, if I reduce the amount of cigarettes I smoke by half from today onwards, what is the probability that I'll be coughing, right? Or counterfactuals, which is, for instance, if I never smoked, would I still be coughing today, right? So what we're trying to answer is not so much not so much whether you can do causal reasoning in general, because of course you can. In fact, causal reasoning, the main thrust of development have been with these Bayesian networks, using them. What we're trying to understand is taking these Bayesian networks, if you only have this circuit, how much causal reasoning can we do? Unfortunately, it turns out that there's some negative answers for this, okay? This is in a recent NeurIPS workshop paper, and another NeurIPS paper we have this year is looking at all of this research that I talked about has been trying to explicitly construct the hypothesis or the model, right? Explicitly construct the structure, regardless of whether the structure itself is interpretable. As I mentioned, you could have an interpretable structure like a program, or you could have something that's uninterpretable like these probabilistic deep networks, but nonetheless, you're constructing an explicit hypothesis. So what are the advantages for machine learning if you don't construct an explicit hypothesis? What if there's a way to keep this hypothesis implicit, okay? And we actually show that we get some really interesting results regarding learning when we leave this implicit. And in fact, we show that, in fact, we can deal with a very rich fragment of logic to get these results. So this is from a NeurIPS paper that I'm happy to talk to about offline as well. So for the last part of the talk, I want to kind of discuss some work where we're doing, applying these models to ethics. So ethical AI is a big topic, and I certainly won't have the time to mention all the dimensions here, but some of these things were mentioned this morning. For instance, this notion of fairness, accountability. There is the notion of responsible deployment. So for instance, if you construct a machine learning model, how are you deploying it into society in a responsible manner? There are all of those kinds of issues, but the kinds of ethics that I'll be talking about really here is two notions. One I will just briefly mention is this notion of fairness. Now, fairness is a very big topic, and basically there is often a misconception that machine learning models are unfair. In fact, that's not true. It's usually, or almost always the case, it's the data that reflects some kind of historical and cultural biases. And because of this, the machine learning model that you train turns out to be unfair, okay? So for instance, this is a data set where even though a majority of the applicants were men, the number of women who were denied the credit card application was disproportionately high. Okay, so you could, this is a clear case where there is, the people who are assessing the application are expressing some kind of bias against women. And as a result of this, the AI community has been looking into a bunch of different definitions. And again, there's some, issues with these definitions, mainly because it's pointed out that these definitions are often inconsistent with each other. So there is growing interest and research in the area area, so I'm not going to say the topic is covered. I'll just talk about what exactly we have been doing in this regard. So one of the issues with when you have a definition of fairness is how do you implement it at scale? How do you ensure that the training is robust? And in this regard, we have been arguing for and motivating the use of these tractable models to essentially identify and implement these fair constraints. So what we're doing here is that we're using a kind of test available in these tractable models to identify what we call as all of the attributes and the dependent variables. So often, for instance, if you get a CV of a person, one naive way is if you hide the gender of the person to make sure that it's fair. But of course, this is what you would call as a protected attribute. But you could also have a lot of proxy variables because, in fact, even if you hide the gender of the person, maybe the name, maybe the school that this person went to might have sufficient information to reveal that this person is a woman, right? So, which means that there is still possibilities to actually enforce unfairness by getting somebody's CV if the right fields are not hidden. And so one of the things we've been doing is using these tractable models to kind of identify all of these dependent variables so that we can implement fairness at scale. The one other project we've been doing is what is called as the moral dilemma problem. Just out of curiosity, how many of you have seen this figure or something like this? It's a fair number. So this is actually a thought experiment, going back in philosophy. And what's happening here is that there's a runaway trolley on a track, and you're the person next to the lever, and you pull the lever, and the track and the trolley could divert. So if you don't pull the lever, the trolley on its own will kill 5 people, and if you pull the lever, it actually swerves and kills this one person. Now, this, you would argue, is an extreme example, but recently Germany has considered this regulation where if you are in a self-driving car, it will always prioritize the life of the pedestrian versus the passenger. And if you are the passenger, you might think twice about getting into the car, or maybe not, if you're altruistic. And so there are all of these extreme, so even though this is a very extreme example, the idea is that a system that is making a critical decision might be in a situation where it has to reason about certain ethical choices. And the question is, what is a good way to approach this? So one approach that came up recently is been looking at, again, using this notion of causality to understand and provide some kind of formalization for this problem, even though it's a very difficult problem and it's not meant to be solved, but it's really towards having a shared understanding of the decisions happening inside the machine. Okay, so it's not very involved. What it's basically doing is that you divide up the model to basically say that there are variables and there are certain actions which affect the outcome of these variables. So for instance, T1 here is capturing the idea that people on track 1 die. And of course, its value will be 1 when you don't pull the lever, right? So when A is 0, and its value will be 0 when you do pull the lever, right? So this is a very simple model to capture the domain. And the idea is that you define a notion of blame that really attempts actions with lower cost. And these costs are meant to capture the kind of tricky decision-making that you would find in this situation. So we took this model and we tried to understand, again using these tractable models, how can you learn models of these model scenarios, and can you compute these judgments tractably? And in fact, we show that the tractable models have a very nice way of tackling these problems. So what's really happening here is that you're taking this causal information and you're constructing one of these networks. So for instance, you can see various equations here which say, what happens if you pull a lever, you don't pull a lever, and so on and so forth. And you learn these costs by surveying people, okay? To see what happens from this, so this is an experimental setup where your best friend is on the main track, okay? And on the side track, you have all of these different options. So you have 1 person, 5 people, 100 people, a pet, and a family member, and whatnot. And what you can see on the left-hand side is the survey answers, and what you see on the right-hand side are the predictions from a model, which are purely learning these costs and applying this causal, this notion of blame to this data. And you can see a very strong alignment. For instance, if it's one person on the sidetrack, most people will choose to save the best friend, of course, so they will pull the lever, right? If it's a pet, for instance, they will often choose to sacrifice the pet rather than harm any person. And if it's a family member, you see that actually people and the machine predicts that that they would maybe even consider sacrificing themselves. Okay, so what are the implications of this model? Again, you see that there is a very strong correlation between the survival rate of a person and the learned utility function. And the idea here is that it's not meant to be a prescriptive model. Okay, it's not meant to say this is what we should do. It's rather meant to say that if it's a kind of a shared computational framework between the man and the machine, and a kind of understanding where exactly is the boundary and the differences between the two systems. So even if it is the case that the system itself doesn't really understand the context beyond these variables and actions, you still have a way to contextualize the decisions the system has taken. So automatic decision making, I think in general, as we see in the case of fairness, is extremely useful, especially, for instance, in a society if there's historical and cultural biases. Machine learning can provide some insight about what patterns we see, but they lead to such philosophically problematic domains that we don't have clear answers to, and this is something we should be thinking about. As a person who, as a computer scientist who enjoys formal definitions, I have to admit that these formal definitions may be problematic, and in fact, certainly some of the discussions emerging in the fairness area are pointing out that these definitions are problematic when applied in society. But my view here really is that these models may provide some insight on how we can see if there's an alignment between humans and machines, or human decision-making and machine decision-making, even if the machine decision-making is in some sense not extremely sophisticated beyond a simple computational mechanism. To kind of summarize, what I've been talking about, I would say that all of these three topics, the notion of explainability, the notion of robustness, and the notion of responsibility, are extremely challenging topics. We certainly don't have good answers yet. And the idea really is that my feeling is that using symbolic logic and logical frameworks really provides you the kind of crisp and systematic way to specify, interpret, and contextualize some of these machine learning models. The broader aim really is the idea that you want data science to be democratized so that everybody can use it, and to get machines, or at least provide an interesting way to integrate human in automated decision making so that they can provide inputs. It does help that we have some kind of interface for humans to suggest what they're thinking about and what they get from the machine. So on that note, I'd like to conclude, and happy to take questions. Thank you very much.